The problem statement from GATE Physics 2018 reads as follows. The logic expression which has been written here can be simplified to, the four options are A XOR C, option B A and C bar, option C 0, option D 1. So essentially we have to solve the logical expression which has been written here, and we need to simplify it to the lowest possible, easiest terms. So we'll do that. First, let's have a look at the truth table for some logic gates. So for instance, on the top row we have the name of the logic gates, namely NOT, AND, OR, NAND, NOR, etc. And below that we have the algebraic expression for them. So for instance, NOT is denoted by the input A followed by a bar on top of the input, and AND is denoted by the two symbols, input symbols written side by side, or sometimes it's also written as A dot B. This dot denotes the multiplication. NAND is interesting. NAND is nothing but first you do AND, so you multiply A and B and then you take a bar of it, hence the name NAND, not AND. So and the symbol also justifies it. So we have an AND symbol, and after that we invert that, so that this circle that you see is taken from this NOT symbol. So that's the NAND. Or is A plus B. It's noted algebraically this is written as A plus B, right? And similarly NOR is also that we first do OR and then we invert it. So A plus B, we first do OR and then finally whatever the result we invert it, correct? Similarly for XOR expression is actually, this can be written as A B bar plus A bar B, right? So every logic gate, these are the most commonly used logic gates, have an algebraic expression associated with them and correspondingly a truth table. So what is a truth table? In the truth table we list all the possible combinations of inputs. So for instance, let's take the case of AND gate. Okay, in AND gate there are two inputs A and B. So the four possible combinations are A is 0, B is 0, A is 1, B is 0, thirdly B is 1, A is 0, and fourthly A and B both are 1. And then we try to find the output for each of these inputs, for each of these sets of inputs. For instance, so when A is 0 and B is 0, so the output is A times B. 0 times 0 is nothing but 0, hence we get the output 0. This again, multiplication in the second row we get 1 times 0, so 1 times 0 is nothing but 0, hence we get a 0 here. Thirdly, 0 times 1 is nothing but 0, and hence you get a 0, this third row. Fourth, 1 times 1 is 1, and hence this output you see as 1. So I just as an illustration I have created the truth table for an AND gate. Similarly, just by using these algebraic expressions that we have, we can obtain the truth table for any gate and even for complex combinatorial circuits. Okay, we can obtain any truth table because truth table is nothing, you list all the possible combinations of inputs and then you just simply follow the Boolean algebra and you will populate the output column. That's all. In this question we were given that this is the expression, and let's say we are required to find the value of this expression, the simplified expression, and I've assumed that the output is y. Okay, so now what I'll do is that let's just have a look at the first two terms here. So in the first two terms what I'll do, I'll take A bar C as common from the first two terms. See, A bar and C both are common, so I'll get B plus B bar. So this is the result for the first two terms. Similarly, from the last two terms I can take AC bar as common. Note, AC bar is common in the last two terms. So I take AC bar common, and what's left is B plus B bar. That's all that's left. Now from these two terms I take B plus B bar as common. Note that B plus B bar is common to both. And what would be left with? A bar C plus AC bar, correct? Now let's first evaluate what this term comes out to be, B plus B bar. Okay, so let's just assume that x is equal to B plus B bar, and let's try to find the value of x. So I'll do the same thing. The input is B, and x is nothing but b plus b bar, correct? So what I'll do here is that, so this is b, okay. Let's try to find this. Let's try to populate this truth table. So there are only two possible combinations, either b is 0 or b is 1. So if b is 0, b bar would be 1, and if b is 1, b bar is 0, correct? Now let's try to evaluate the value of x here. X is nothing but b plus b bar, so it will be 0 plus 1, which will turn out to be 1. 0 plus 1, we know in Boolean algebra it's 1. In the second row, we see x equal to b plus b bar. So the value of b is 1. The value of b bar is 0. So 1 plus 0, it will again turn out to be 1. Now, this is an interesting case. Whatever is the value of b, note that b can only have two values, 0 or 1. So whatever is the value of b, the output x is always 1. So this is always true. X is equal to 1 irrespective of the input. So I can write x equal to b plus b bar equal to 1. It's independent of the input. It's always true. Hence, now if I come back to my original expression, what I have obtained is b plus b bar equal to 1. Note this. Let's put this value here. So I'll get y equal to 1 times, note that the value of b plus b bar is 1 now. So that will be a bar c plus ac bar. So we'll get a bar c plus AC bar. Now note that this is nothing but the algebraic expression for an XOR gate, 2 input XOR gate with inputs A and C. So we see that. So I told you the XOR is nothing but A B bar plus A bar B. Here one of the inputs is C. Instead of B, it's C. So A bar C plus AC bar. So what we get is an XOR gate. Right, so this was the question, and we simplified it, and we obtained that this logical expression can be simply written as A XOR C. Option A is the correct answer. Thank you for listening.